Hello, DVCon 2021. My name is Eldon Nelson, and I'm a field application engineer in verification group at Synopsys. I'm excited to talk about this topic today because I think it's going to bring together two different audiences. Of course, we're in the formal track at DVCon right now, and so I expect there to be people listening who are accustomed to formal and some of its applications. But since the title includes the word synthesis in it, I'm hoping some of our back-end synthesis friends will come along for the ride. What we're doing in this paper is trying to look at, are there ways that you could reduce the amount of logic gates, that are required to implement a particular logic function if you knew how that logic was actually used in the field. So reducing gates is a great goal. It's a goal that could reduce power, it could reduce die area, and eventually just reduce costs for the consumer and also for the producer. Since I'm hoping we have this bifurcated audience of different skills and experiences, we're going to be covering some of the terminology. Then we're going to cover why this is an interesting idea to propose and the use case for it. We'll cover the example DUT that we'll use called tinyALU. We'll go through our method, results, and summarize. We're going to define RTL as System Verilog as our design language today. And gates is going to be a gate level netlist, and that's going to be also in System Verilog. Now we've expanded the two module definitions of single cycle in this case. On the left is the System Verilog regular implementation, but on the right is also System Verilog, but it's a gate level implementation that's targeted at a specific fab technology. And so we come to that technology that connects RTL to gates, and that's generally known as synthesis. I'm a little nervous about talking about synthesis because I work at Synopsys, and our co-CEO, Art DeGus, is one of those guys who's done a lot of work in the synthesis area. And so I'm nervous about what I'm proposing here, but I think this is a very interesting approach, and it's a technology that I don't think existed when Art was working on these early synthesis compilers. The way to think about synthesis is that it's a very excellent Boolean reduction tool. It can look at RTL and any complicated expression you might have done that describes combinatorial logic, and it can simplify it down to the most efficient representation in the gate level technology from the fab that you're given. And it even has built-in techniques that I assume all the vendors implement, where it can optimize logic based off of constants. The Synopsys synthesis tool uses a command called setLogicHigh, or setLogic0, to tie primary inputs of a design to 1 or 0. You could also theoretically tie internal nodes of the design to 1 or 0 also. And by doing this, when synthesis runs, it can recognize those constants in those Boolean equations it's trying to implement and use that to simplify down the logic. This is useful sometimes when you have a design where you can just tie one of the inputs to put it in a particular mode. And then when synthesis runs, it recognizes that mode, and that logic is propagated through all of the final gates of the design, and you get the design that you're looking for. Constant propagation does have the problem that it's constants. It's not complex relationships between signals. For example, you couldn't say that there's a one hot input signal. And you definitely couldn't do something saying that this signal is 3 1s in a row followed by 3 0s in a row. And those relationships could not be used to simplify the design. All right, so we've covered a lot of what synthesis is about, RTL netlists and gates, and now we get back to the formal world. And so to explain this part, we have to talk about what formal coverage analysis is. So formal coverage analysis is a subset of formal. And what we're doing is we're trying to see, depending on the stimulus we give the design, what parts of the RTL is reachable, what parts are toggleable, and all sorts of other code coverage type metrics. The way that we can tell formal coverage analysis what are the available or valid stimulus for the design is with the assume statement in System Verilog. And of course, this assume statement can describe almost any type of behavior very elegantly, very quickly. Unfortunately, the assume statement is not used by current synthesis engines. RTL designers have techniques also that can help them realize their designs as efficiently as possible. They have the System Verilog define, parameters, generate statements. All of these can help reduce the amount of logic from the base to something specific and targeted for what they're looking for. The problem is, it's going to be a lot of work for the designers to efficiently use all of these techniques. And there might be sometimes optimizations that just aren't done because it's just too specific, and they want to keep the code base simple and easier to read and maintain. There's side effects and inefficiencies of interacting parameters and if-defs. When you make something that's parameterized and has defines in it, you have to make sure that they can all work together through all the different combinations. It creates this huge burden up front to validate that all the combinations of the parameters and defines will work together. When we talk about realizing a design in gates, we have to realize that every single feature, every ability that logic has a feature cost. And that cost is sometimes very hard to quantify. The only way you could do it now is with all those designers, parameters, and defines, and allowing the synthesis engine to use that smaller logic to realize the design. But if you kept asking the designers for more and more parameters to turn off more and more of these pieces and features of the design, it will quickly become out of hand. The parameterization and the define methodology that designers use today can't keep up with that. Can't keep up with the infinite number of things you could try. For example, to see the cost of what if we only added even numbers with our integer, and asking a designer to put that parameter switch in, it would create totally different logic. If you only allowed memory operations to never be back to the same address, that might result in a different type of logic. It might reduce some of the logic that tries to avoid those types of patterns. What if you removed an operand entirely from a design and asked the designer to tell you how many gates exactly that would take, how much power that would take? These are all very interesting questions to ask designers, but I don't think they want to answer it for you. It's too much work, it's way too specific, and it takes them away from designing the big idea. Here is what the paper is really about. It's the why do this method. Why would we ever want to try to optimize the design in such a way? And how could we get these reports in a way that's not entirely unbearable? Deep optimization of design for a particular application can reduce power and can reduce gate number, which is the area. And that's a huge thing that we want to pursue. Realizing those deep optimizations is sometimes not worth it. And even trying to attempt to do those deep optimizations, it's not clear if it would result in any optimization. The amount of effort required may do nothing, and that would be a terrible waste of resources. Requirements can change in the middle of design. It might be a completed design used on the next project that doesn't need a particular feature. And so that feature is just carried forward as a vestigial piece of the design that you're not removing because it's too much work to remove it, to test it all over again. But if there's a way where you could remove that logic that you didn't need because of your use case, that could save you area on the die. And this general request to reduce gate count, I've actually seen it on customer designs where the design lead realizes at the very end that in order to fit on the die, to ease up the burden for timing closure and all the physical design, all the back-end constraints, they just need to reduce gates a little bit. Won't be a very efficient way to do that. This paper tries to describe a way where you could do that in a very fairly automated fashion. So to talk about the problem in a very concrete use case, we're going to be using the tiny ALU. I'd seen this example in Ray Salemi's UVM book called the UVM Primer. And the way that this tiny ALU works, that we'll be covering going through the methodology and the example, is it has two inputs, A and B, and an operand, which is a 3-bit vector. And those two inputs, A and B, are either routed to single cycle operations, which are ANDs, ADDs, or XORs, or it's one of the 3-cycle operations. There's only one. It's called multiply. And depending on which operand and input you have, the result goes out to result, and the done and start flags control the flow. This is the operand table for tiny ALU. Every operand has a value that is used to decode what is going to happen. Earlier, we were talking about constant propagation in synthesis. That would allow you to put some of the inputs to constants and then allow synthesis to figure out how to reduce logic based off of that constant value. In this case, we can actually see bit 2, the most significant bit, if we tied that to logic low, then we could actually get rid of op XOR from being a possible input. If you tied the most significant bit of the operand to 0, it would actually remove the XOR logic from the design. Synthesis is that smart. But in this case, we want to remove a function of tiny ALU to illustrate the process. What we want to do is we actually want to remove the op mult operand, and we want to allow formal to tell us how to remove that in the most efficient way. In this case, there's no constant that you could put on the primary inputs of tiny ALU to get rid of op mult. It doesn't work with the constant propagation trick that we were talking about. If our goal in this exercise is to remove all of the logic from the multiplier operand, how would we do it? In System Verilog, the assume statement can describe the constraints of the stimulus. And we could use this line to say that the operand, the port name was op, is never equal to op mult. It could be any other value except that one. And this is a really nice way of being able to do those what if statements. This is a very succinct and simple way of describing what happens if you said, I don't want to do this particular operand. What logic could I remove? The example code and the methodology from the Synopsys tools is available at this URL here. And you could download that from GitHub, and then you could run the make files and look at the source code that we'll be talking about in more detail. When you download the repo onto your computer, you can actually run this make target, and you could see all of the different commands that are involved in running formal on this design. When we run this make target, it's going to run VC formal with no assumes on the primary inputs. And so when it runs, we get all of the RTL lines of the entire design are reachable. So now let's look at the flow diagram, a zoomed in view of part of it. And what we're going to do is we're going to start at start, and we're going to bring in the design on the left, and we're going to do formal code coverage analysis with the stimulus assume statements. These assume statements are the ones that control what is the possible state space of the stimulus. And then we're going to identify unreachable lines caused by the assumes. We don't need to identify lines that are unreachable for some other reason. We want to look at ones that are only caused by the assume statements. Then what we're going to do is we're going to take the design and comment out all of the unreachable RTL lines caused by those assume statements. We'll have a new RTL that's edited with just comments. Then we're going to run synthesis and we'll have a synthesized netlist. When we run that flowchart doing VC formal analysis with the stimulus assume statements on it, we can get that lines 115 through 123 are unreachable because of those assumes. We can use this information to figure out what we should comment from the source RTL. Commenting is pretty easy. The tool gives us the lines that we need to comment, and we literally put the system verilog comment statement in there. This process can be automated because VC formal, when it creates the unreachable lines, can write out an exclusion file that tells us what we could get rid of. And using scripts, this process can be automated to automatically remove these lines for you, making this an automated step. With the example code, we can run synthesis two ways. One, the original vanilla design, and two, with our edited RTL that commented out those lines in question. When we run those two make targets with and without the commented lines, we can see that the top one took 520 gate level cells to implement the original design. After we did our comments, now the design only takes 127 cells to implement. All the other metrics kind of flow from that cell count, the different types and sizes of all the cell libraries. And we can get a 4x improvement. Of course, multipliers take up way more logic than doing an AND or an XOR. And so this kind of makes sense to us. So is that the end? We use an automated process by describing what valid stimulus was possible, and we were able to automatically remove logic safely from the design. Can you go farther? In fact, you can. You can actually do another round on the design. If we look at the flowchart here, we're going to start with the synthesized netlist that was created in part one that had the reduced logic on it. Then what we're going to do is we're going to put in the stimulus assume statements, and this time instead of running line coverage, we're going to be running toggle coverage on the design. And we're going to see other toggles that are not possible anymore because of our stimulus assume statements. And if those toggles are not possible, we can actually tie up or tie down in the gate level netlist those signals. And then we can put it back into design synthesis. Remember, synthesis is very smart about realizing that there's constants in the design, and tying a node up will allow synthesis to actually reduce logic safely and recursively as it goes through. And we will get another optimized synthesized netlist. In this screenshot, VC formal was run off the optimized netlist from the first synthesis. And this time, instead of looking at line coverage, we're looking at toggle coverage. There's one toggle in this tiny ALU design on the net called N60. The N60 is just an arbitrary name that Synthesis has come up to auto-name nets. And it says that net N60 cannot toggle from 1 to 0 ever. It is stuck at 1 all the time. So what we're doing now is we're going to look inside the net list. And here we've looked inside and we found that N60 is the output of an ND2, decoding what these library cells are. This is a NAND2, so it has two inputs, A and B, and then they're NANDed onto Z, which is the output. So the driver of N60 is whatever that equation is. But we don't care what the equation is because we know that whatever A and B are, it's always going to make N60 always equal to 1. So if we comment out that driver of the net, and then we assign N60 to 1, we can allow synthesis to go through and clean up everything. We're going to run synthesis the second time with that gate level netlist edit. Now with this toggle remover, we were able to remove a little bit more. Now we're down to 103 cells to implement the logic without the op mult command. All right, so here's the entire flow in its entirety. You can see there's two separate synthesis runs. In the first run, we're looking at RTL and doing line coverage with our stimulus assumes. The second time, we're still using the very same stimulus assumes on synthesis 2, and now we're looking at toggle coverage to figure out things to do tie-ups or tie-downs to. One of the main ideas behind this approach is we want it to be something that's automatable. We don't want a lot of human interaction. And so to make it easier, we want to do line coverage with the RTL. Some of the benefits are it's easy to comment lines with a script. You don't have to rewrite RTL or do anything fancy. And signal names are still available with the original RTL. For example, all the design ports and even internal port names are still accessible with the assumed statements that you might be writing to constrain your stimulus in a certain way. So the question comes up, why don't you just do line coverage with gates? Well, the easy answer is line coverage does not exist in a gate level netlist. A gate level netlist is purely structural, and structural netlists actually have no line coverage as we measure it. Why do we use toggle coverage analysis with the gate level netlist? Again, it's very similar to the ease of use problem. In RTL, it's very easy to comment lines of code. But in toggle analysis, if you're given a toggle that's part of a vector, maybe a slice of a vector, and you have to unwind that out of the RTL, that's a very difficult thing to do in System Verilog. You'd have to rewrite that array, that slice, in many different parts of the design, and it would probably result in unreadable code, and also trying to break an array for slices being tied to 1 or 0 is very difficult to do. When we do these optimizations, it's very important to realize that what we're doing is we're actually removing logic that responded to certain stimulus patterns. And when we've removed the response for certain stimulus, completely just obliterating it from the gate level netlist, we've actually created a design that cannot stand or cannot operate correctly if you give it the stimulus in question. For example, in our tiny ALU example, we said it's impossible for this design to ever get an op mult. And I want this process to go through and remove all of the logic automatically that had to do with that particular operand. And so now if you actually sent in the operand op mult, it's actually unknown what the behavior would be to respond to that stimulus. And that's not necessarily a problem because the whole exercise of this was we wanted design specifically made to work with a stimulus that we were going to give it. Throughout this paper and presentation, we've gone through a method that looks at how you could take the allowable stimulus of a design to optimize the gate level implementation that was derived from it, to reduce logic to save power, area, performance, and better match what the end user needed of that logic. There's a lot of concern taken to make sure that this methodology is automatable, has very low human effort required to do it. And those decisions just made the process, I think, a lot better. So what you could do with this idea is, of course, make designs smaller, less power, less area. But you'd also do the what-if scenarios, where you could see how much does every feature of design actually take as far as gates required to implement it. It's something that a designer would dread doing. There are different types of code coverage that we didn't cover in this presentation. Notably, I think condition coverage, if used, could figure out a few more optimizations that are not covered here. There's more work to refine the scripting flow and perhaps future products that use this methodology. I'd like to thank Alex Nettering at Synopsys for meeting with me multiple times talking about this idea. I'd also like to thank the volunteers Xiaolin Chen and Michael Poplinger, who at DVCon reviewed a lot of these early papers and helped me with these slides too. I really enjoyed sharing this idea with you at DVCon and hope you have a great day, and please vote for best paper.